we're looking at is the mass that we want in the moderator of a thermal nuclear reactor such that it transfers kinetic energy from the fission neutrons to slow them down to become thermal neutrons as efficiently as possible, so with less collisions. Now, so what we're really looking at then is a scenario where what we're going to be doing is we're going to be taking a neutron and it's going to be smacking into something. I'll call that before. And the mass of that neutron, I'm just going to say it's got a mass m. And I'm going to say the velocity of that neutron's got a mass v. I'm just going to call, right, the neutron is A, the thing it's smacking into is B. Now afterwards, we've still got A and B. Rewind slightly, the mass here we've got to decide on, so I don't know what that mass is going to be. We're going to consider different masses. And the velocity here initially, we say it's smacking into something that's stationary. Now afterwards, we know the mass here is going to be m. The mass here is going to be the same, whatever it was before, the mass won't have changed. The velocity here we don't know, and the velocity here we don't know. But what we do know through this collision is that momentum must be conserved, and these will be an elastic collision. An elastic collision means that through this collision, kinetic energy must also be conserved. So momentum obviously is mv, kinetic energy is obviously half mv squared. Alright, so the total momentum before must equal the total momentum after, total kinetic energy before must equal the total kinetic after. So we're going to be providing this neutron, which is going to have a mass of 1. And we're going to look at a couple of scenarios and try and figure out what's going on. We're going to look at the mass of the moderator, which we're going to look at 1, 2, and 3, and kind of see if there's a trend that carries on. And we're going to look at the percentage of the kinetic energy transferred. Okay, and that's what we're going to be considering as we go through. So, let's consider the first, and probably the easiest scenario. So what we've got before is the neutron. So there's my neutron. I'm going to call it A. There's my moderator nucleus. Call it B. I'm going to say the mass here then is 1. The mass of the thing it's bumping into, the moderator, is going to be 1. My velocity here is 1, and initially, sorry, it's going to be V. And initially, I'm going to say that this thing is stationary. It's bumping into. Now, afterwards, what will have happened? Well, A, B, the masses are still going to be the same. They won't have changed. But I've now got this moving at a velocity A and this moving at a velocity B. And I don't know what they are at the moment. So, let's work through. Firstly, we know must be conserved with my momentum. So I know, let's rewind ever so slightly. I want a mass m here because I don't know that it's 1. I'm going to call a mass m, so we'll make all of those m's. So they've all got the same mass, 1 unit. So momentum here, my momentum must be mv, and that must afterwards be equal to mva plus mvb because momentum's conserved. Now you can immediately see that my masses have cancelled. It's irrelevant because they're all the same. So I know the velocity before must be equal to the velocity of A. The velocity of A before must be equal to the velocity of A plus the velocity of B afterwards. If I consider kinetic energy, I know half mv squared is the kinetic energy before, because that has kinetic energy, that has none, it's not moving, must be equal to half mva squared plus a half mvb squared, because both particles are now going to be moving. We don't know how fast, or actually indeed if they are moving, we just know that's what their kinetic energy would be. So if I look at this again, I can simplify because the half m's all cancel, so I know that v squared must be equal to va squared plus vb squared. Now I've got two simultaneous equations that I want to work with. And what I'm going to do is I'm going to substitute for v here, because I know V is equal to VA plus VB. So I can write VA plus VB squared must be equal to VA squared plus VB squared. Literally substituting in for V from this equation. So that gives me VA squared plus 2VA plus VB squared is equal to VA squared plus VB squared. Now I can cancel and simplify down. I can take VA squared off of that side. I can take VB squared off of that side. So I've got 2VA/VB must be equal to 0. Now that tells me either VA must be equal to 0 in the solution, or VB must be equal to 0 in the solution. Now if I look at what I'm considering, I've got something coming in, smacking into something that's stationary. Well, the thing that's smacked into must end up moving. Alright? So I know VB is non-zero. So if VB is non-zero, so VB is not equal to 0, then VA must be equal to 0. So if VB is non-zero, VA must be equal to 0. I know VA plus, V is equal to VA plus VB, going back to this equation. So I therefore know, if I know VA is 0, V is equal to VB. So in the model I've got here, I know that VB is actually equal to V, and VA is equal to 0. So this particle comes in, actually a neutron, smacks into a neutron or proton nucleus. The incoming stops. The other one flies off at the initial speed the first one came in at. And that is our solution. Now if you think about this in terms of what's involved, here 100% of the kinetic energy was in particle A. Afterwards 100% of the kinetic energy was in particle B. Therefore 100% of the kinetic energy is transferred when the neutron mass is the same as the moderator mass. Now to be clear, you've already considered this before. This is a classic Newton cradle scenario. Right? You have this scenario. These are all stationary. One comes in. That's moving. Out the other side then, you're going to get 3, 4 are still going to be there. One out the other side goes flying out. So it's classic Newton's cradle. You've been familiar with this sometime. Now, we're going to consider the next most complicated scenario, or next simplest scenario, depending on how you want to term it. So what we're going to look at then is a scenario where we've got before and after. Now this time, still particle A, particle B, or nucleus A, nucleus B. In this case, A is the neutron still, so here I've got a mass, and it's going to have a mass m. It's coming in again with a velocity v. The difference this time is the particle it's going to bump into, I'm going to say, is going to have twice the mass. Now, afterwards, they'll still have those same masses. The velocity here, I'm going to say again, is stationary, but I don't know what the velocities are going to be the other side. And I've got to figure it out. So again, momentum must be conserved. So I've got mv must be equal to mva plus 2mvb. And I can simplify through again, for m, which gives me v is equal to va plus 2vb as my first equation. Kinetic energy is going to give me my second equation again. So I know half mv squared must be equal to a half mva squared plus half 2m, because it's got twice the mass, times by vb squared. And again, I can simplify down. The halves can go away, the m's can go away. That gives me v squared must be equal to va squared plus 2vb squared. So I've got my two simultaneous equations again that I am going to solve. So I'm going to substitute for this v, for va plus 2vb. So I've got va plus 2vb squared must be equal to va squared plus 2vb squared. I'm going to expand this. So I'm going to get VA squared plus 4VAVB plus 4VB squared has got to be equal to VA squared plus VB squared. And I can simplify that down. First off, I can get rid of the VAs. They're gone. Sorry, that's 2VB squared from there. Mustn't lose that. I'm going to take 2VB squared off both sides. So I end up with 4VAVB plus 2VB squared has got to be equal to 0. Now I can simplify it down a little bit more because I can get rid of the VB squared. So I've got 4VA plus VB plus 2VB is equal to 0. I can simplify again, factor of 2. So I know I've got 2VA plus VB is actually equal to 0. Switch those around. I know I've got 2VA is equal to minus VB. Or put another way, VA is equal to minus a half of VB. So what we're really saying now is we've got a scenario whereby A and B are going in opposite directions. And B, I'm going to say is going that way, is going twice as fast as A, which is going in the opposite direction. Okay? Now, we're going to work through that just a little bit more and see what that actually means. So if I look at this, going back up, I've got V is equal to VA plus 2VB, back from my initial equation I had up here. And I'm going to substitute for VA. So I know V is equal to minus a half VB plus 2VB, just substituting immediately from up here. That gives me V is equal to 1.5 VB, which if I flip around is going to tell me VB is equal to 2/3 of V. So B here is moving at 2/3 of V that direction. And we know that VA is half as big as VB, going in the opposite direction, so that must be 1/3 of V going in that direction. So, if we're going back, we now know that VA is equal to 1/3 of V, and we know VB is equal to 2/3 of V. So, VA, should say minus there, but it doesn't really matter. If we look at the kinetic energy, what I've got then is a half mVA squared is equal to a half mV upon 3 squared, because I know what VA is. Therefore I can say it's a half mV squared upon 9. So initially I had a half mV squared energy in the neutron, in the fission neutron. I've now got a half mV upon 9. So I've now got 1/9 of the kinetic energy. So particle A has 1/9 of the kinetic energy. Particle B has the other 8/9 of the kinetic energy. Therefore, in terms of what's transferred, I've transferred 8/9. So I've transferred 8/9 times by 100. 8/9 times 100 is going to give us a percentage. 8 divided by 9 times 100 gives us a percentage of 88.8 recurring, so 88.9%. So by swapping, let me just put the number back on here so we can see it. If I can find the right piece of paper, that is. There we go. So I've got this is 88.9%. So when the neutron has the same mass as the moderator mass, 100% of the kinetic energy is transferred. When the neutron has a mass of half that of the moderator, 88.9% is transferred. And if you actually work this through to number 3, you get 75%. And these numbers, funnily enough, would keep getting smaller. So we know, in terms of the kinetic energy transferred for moderators, we want, for optimal efficiency, the mass of the moderator nucleus to be equal to the mass of a neutron. Now, from broader conversations, you know that's not ideal, but I'm not covering that here. Hopefully that makes sense. Thank you very much.